Okay, in the next section I want to talk about is categorizing the hypothesis. And the idea is, what type of problem are you trying to solve? So here's an example of two different problems. The first one, let's say the loan department at Clear Lake Bank wants to decide which customers to lend money to. And some customers are reliable, pay off the loan. Others may default on the loan and the bank loses money. So the question is, do customer demographics such as age, salary, number of children help relate to whether a customer is a high-risk loan applicant? So that's one type of problem. Another type is, let's say the dean at the university wants to see whether graduate student demographics can be used to predict a student's final graduate grade point average. So the hypothesis might be, do students' demographics such as age, SAT scores, GRE, undergraduate GPA reflect upon a graduate student's final grade point average? And the hypothesis might fit into one of several categories. For regression, we take data and try to come up with a real value prediction variable. So for example, let's say we have a simple example here, raw data x, y, and this line separates the z's. So the idea is, how does x and y relate to z? Well, it's kind of a trivial one. It's basically x plus y squared gives us z. And so we don't know that initially we start out, and our solution would be some type of polynomial equation, as I show there. So regression, you can think of it as curve fitting. Classifier, what it does is try to build these different classes, and the final result might be a decision tree. So this is an example of drivers. So if a gender, we start with the gender. If the gender is female, they're low risk in terms of driving. If the gender is a male and they're under 25, they're high risk. And if it's a male over 25 and over, they're low risk. So that's one way of representing a classification tree. We could also represent it as a rule or set of rules. If gender equals male and age less than 25, then insurance equals high risk. Otherwise, insurance is low risk. So it collapsed these two there. Basically, males under 25 are high risk, everybody else is low risk. In clustering, what happens, it tries to group things that are common, and we want to have a lot of synergy within this group here, a lot of synergy in this group here, a lot of synergy in this group here, but very little synergy from this group to this group to that group to that group. And here's an example of what's called a dendrogram. This is used a lot in bioinformatics for gene mapping. And if genes have a lot of synergy, we see a lot of green. No synergy, we might see, or negative synergy, we see a lot of red. Okay, so it's an example of clustering. And we'll see more examples of this in the semester, so I think it'll become clear. There's also what's called an association rule learner, and what it does is it takes, let's say, different attributes and tries to come up with any relationship. So this is what's called, this is the Titanic Data, and it says the crew, there were 885 crew members, and they were all adult. Now that doesn't tell you much, but that's what it does. The crew had 862 males, and they were adults. Here's one, how many males survived? None, 1364. How many adults? 1329, so that's the confidence we have. And of the crew of 885, 862 were male, so it finds a relationship between one or more attributes on either side. The difference between association learner and, let's say, a classifier, the classifier, the dependent variable, or the class variable in this case, is risk, high risk, low risk. Here, in the association, we don't necessarily have any class variable, dependent variable. Anything could be a dependent variable. So here's an example, classic example. Grocery stores might see that people buy soda and potato chips. They buy that together 88% of the time. Maybe people buy diapers and aspirin 68% of the times. And they buy hot dog buns 85% of the time. And an organization might use this, like a grocery store, and say, okay, this is obvious, but put the chips next to the soda, keep the hot dog buns close to the hot dogs, make it easy for consumers to make those purchases. So coming back to the first problem, do customer demographics relate to whether a customer is a high-risk loan application? We might view that as a classification type problem. The second one, can student demographics be used to predict or reflect upon a student's final grade point average? That might be viewed as a regression type of problem. And so the sooner you can understand what type of problem you have, the easier it is to go forward to know what tool or tools to use in that situation. Let's see. Next, once we build a model, we want to be able to describe the results. And here, this is a classic graph created by a mathematician named Minard in 1885. And what we see is it's showing a region, and Napoleon's army is represented by this beige, and going to Moscow, it's in beige, coming back, it's in black. The width shows the number of soldiers that Napoleon had in his army. Notice that it decreases in width, and it decreases because of the fighting or the bad weather. And so he gets all the way to Moscow, and I guess there was a battle there, and he comes back, and you see how thin the line is. By the time they get here, it's about like 10% of the, or even less, 10% of the original line. So it conveys a lot of information. It conveys where the troops marched to, and they had to split off here. It also conveys the loss of life as it goes forward and the path back. So it conveys quite a lot of information. Another graph that shows a lot of information, this was from a website called fundrace.org, and they got bought out, but it's a very insightful graph, gives a lot of information. It's a map of the United States, and you see we've got basically red, white, and blue. The darker the red that is, the more dense in terms of number of Republicans. That's one political party in this country. If it's kind of white, it's showing it as neutral. If it's in blue, the darker the blue, that's the other political party, the Democrats. So we could see, okay, Texas is pretty red here. We also see these pie circles that pop up, and they show the population within a particular city. So New York is about 75% Democratic, 25% Republican. Houston, it looks to be about, 60% Republican, 20% Democrat. Also, the size of the circle is different, which shows, the bigger the circle, the larger population. White is kind of neutral, not real Republican or Democrat. So this conveys quite a lot of information, in terms of the data. Next, we have what's called validation, and that involves you come up with a solution, but you don't know if it's a good solution. So it's usually a good idea to have a separate data set, independent data set, to validate the model. And we want to be able to construct what's called a realistic backtest. That's very important. And a backtest is when you take historical data and you analyze the historical data. I teach a class in financial data mining, and sometimes what happens, there might be a model, but it was applied to a strong bull market. And so you'd expect it to do well if you're trying to predict, come up with long trades or trades when the market goes up. So you want to be able to bulletproof it so it works under all conditions. And then verification, that's validation. Verification is whether the model is reasonable. If a model claims that every time a car goes over the Brooklyn Bridge, a pizza is sold at Pizza Hut, those events might be correlated, but it doesn't mean it's a causal relation. So sometimes things are correlated, but doesn't mean there's a relationship. We also want to be careful about overfitting the data. So here we've got different points, and we might get a solution that generalizes the pattern in the points. Overfitting in this case is we go through point by point by point, and the solution is very locked into that particular data set. If we have another data set, it might not do as well, and the reason is because it locked into the first data set. So the idea is that the solution is very fragile because it's so dependent on a particular data set. Next, we talk about calibration. And it could mean different things. It could mean taking the original model, refining it, and it could be adjusting the original model and also doing some sensitivity analysis. Just because you get a solution does not mean you're done. And what happens if you get a solution, new data comes along, you need at some point to revise or calibrate your model. And so this is something that can go on and on and on in perpetuity. So in summarizing the data mining process, what we do is we observe reality, formulate a hypothesis, establish a goal, define what data or metrics we'll have, collect it, clean it, pre-process the data, build a model or several models, describe the results, validate and verify and backtest, and calibrate, which means revising the model and kind of a little loop there. Things you want to think about as you do data mining, I highly recommend keeping a log and summarizing results. That is, what worked, what didn't work, include actual results, what is significant, how do results compare to other experiments in the same domain, are there any limitations of the model? So I view this as what's called the consciousness of research. And it's important to keep a log because here's what can happen. If you're working for a company doing data mining, you might do some experiments for the next couple of weeks, and then you put it aside, you come back a year from now and say, well, what did I do? So you want to be able to refer back to the log and save yourself from having to do all these repeating experiments unnecessarily. Well, we'll stop here before going on with the remainder of the notes.